Ron Brightwell is at Sandia National Lab. He's a manager of the Scalable Systems group or division. I don't know what to call it.
Scalable System Software.
Yes, and then he has been, I know of him as the communications czar at Sandia. When I knew him, he was doing Sunmas, and then there was Puma, and then there was Portals, and Portals is probably where most of you know him from. And then he has been involved in the exascale computing project in various projects of that as well, and so a leading figure in the extreme scale computing community. And he's going to talk about resource management, which is of course a topic that we all hold dear in this community here. And so, let's see, we're eager to hear him. Ron?
I'm eager to talk. Thanks, Sanjay. I appreciate the opportunity, I appreciate the invitation. I'm glad to come talk to this group. So what I'm going to be talking about is resource management challenges in the era of extreme heterogeneity. One of the reasons I wanted to come present this topic is because this is, I think, highly relevant to what's going on with Charm++ and the work that Sanjay and his group have been doing. Here's just a brief outline of what I'm going to cover in this talk today. One of the challenges that I've always felt when I hear keynote talks is what exactly I'm supposed to take away from a keynote. I don't know if you guys have had that impression in 22 years of going to talks since I've been at Sandia. I sit through keynotes sometimes where there's some really interesting stuff, but it's not relevant to what I care about sometimes. And a lot of people spend the majority of their slides talking about what they're doing, and then they give you 2 slides on how what they're doing relates to you in some way. I hate those kind of keynotes. So I'm hoping this keynote will actually be what I'm going to present is interesting and relevant to you. I'm hoping it's going to be a little bit interactive because I really kind of want your perspective and feedback on some of the stuff that we're doing because, again, I think it's highly relevant to what you guys are doing. So I'm just going to give you a couple of, give you a brief takeaway, what I expect, what I'm trying to accomplish. Then if this isn't interesting to you whatsoever, you can just go read your email and surf the web and do that. That's fine. So I'm going to talk just a little bit of context about the national labs. And what our funding models look like. Then I'm going to talk about extreme heterogeneity. We had a summit last year. We had a workshop that was more recent. And then I'm going to talk about some of the priority research directions that came out of that. And then things from my perspective that are concerning to me. And most of this talk is about challenges. Unlike Sanjay, I'm not even going to give you any potential solutions. I'm just going to talk about what the challenges are. And I'm hoping you'll start thinking about some of the ways that Charm++ and some of the work that you're doing actually can address some of those challenges going forward. So here's my key takeaways slide. So we had a recent Oscar workshop on extreme heterogeneity. We identified several key challenges and potential research directions in these areas. So programming environments, software development, sustainability and productivity, operating systems and resource management, data management, analytics and workflows, architecture, modeling, and simulation. In this talk, I'm really going to kind of focus on the OS resource management aspect of it because that's the perspective that I was bringing to the table for this work. The results of this workshop, so this workshop was in January, and I'll give you some more details on it. We're working on a report right now that kind of captures everything that happened during the workshop and how we came about developing some of these priority research directions. The caveat here is that report development is ongoing. So as Sanjay well knows, some of the Oscar reports, you can spend a significant amount of time putting a lot of effort into developing these reports, and they may or may not see the light of day. We're hoping that this one actually has enough visibility and enough importance to go through, to be published. Ultimately, what the Office of Science tries to do then is motivate programs around some of these things. But again, a lot of these things depend on things that are out of our control. Just as a caveat. So it's interesting when I in my management job now, so I've been a manager at Sandia in managing our scalable system software department for about almost 10 years. I do a lot of recruiting, so that's another reason I'm here, because it's always good to go to universities and talk about what we're doing, just as a recruiting aspect of that. The first thing I ask people is if they understand the difference between the DOE labs and the funding models of the DOE labs, and most people don't. They think DOE labs are all sort of the same. And so one of the things I want to talk about in setting up the work that we're doing here is that if you look at the NNSA labs, and so this is the Sandia, Los Alamos, and Lawrence Livermore labs, most of the funding that comes to those labs is through a program that's called the Advanced Simulation and Computing Program. This started out as an initiative in 1995. This is where the first teraflops machine and then all the big machines that came after that. It was called ASCII. It stopped being an initiative after about 10 years and converted to this new acronym. Within the ASC program, there are these different program elements. And so if you look at these program elements, they cover things like integrated codes. And so these are the actual production applications that we use to meet the stockpile stewardship mission. And then we have these other program elements that are there. Most of the ones that affect the work I do, support the work I do, are the CSSE program element and the new program element, which is called ATDM. Okay? Just a brief explanation of those two things. So CSSE is really computer science funded work that supports the large systems that ASC deploys. And so you can think about some of the activities around things like the Trinity system that just showed up at Los Alamos last year. So there's a lot of support work from a CS perspective that needs to go into supporting that machine. And so there are projects like OpenMPI for Trinity that Los Alamos and Sandia work on. That gets funded out of CSSE. The newest program element is ATDM, and ATDM started about 3 years ago, and it was a recognition by NNSA that future advanced technology systems, so these big systems like the Sierra system at Livermore, were so different that our production codes, which were essentially MPI everywhere, were not really well prepared to take advantage of those platforms. And so ATDM was sort of started as I want to say a start from scratch approach to how to make our production codes work on those types of machines. So many core heterogeneous kinds of machines. ATDM also ends up being the NNSA contribution to the exascale computing project, which I'll talk a little bit about. The important thing here from a funding perspective is we get a budget that gets allocated to ASC at the lab, at the tri-labs, and we tell headquarters how we're going to spend it. So you can think of this as base funding, right? We don't ask for this money every year. We don't propose for it. It gets budgeted to us to support the stockpile stewardship mission. Okay, so it's a very nice funding model because it allows us to sort of be strategic about how we want to make that investment. We can look out a little bit further and see down the road what's coming and how our codes are going to have to react to it. But it's not soft money. It's budgeted to us. The budget can fluctuate every year, but then we essentially tell ASC headquarters how we're going to spend that money. So this is in contrast to the DOE labs, which you can think of as the science labs. And so this is Argonne, Oak Ridge, Berkeley, PNNL, several others. They're funded by the Office of Science. They have multiple program offices in the Office of Science. The one that probably most of us in HPC are familiar with is the Advanced Scientific Computing Research Office, which is called OSCAR. It's great to have ASC on the NNSA side and ASCR on the Office of Science side, just to make the acronyms really confusing to people who don't work in the DOE environment. They really have a science mission, so they're not sort of aimed at any specific application area. And they have a program funding model. So typically what happens is a budget will appear at the Office of Science. Then the program managers at the Office of Science figure out how they should be making those investments in future research programs. And the community kind of helps them do that. But then when they actually have a call, it's a competitive proposal call. And so this is the kind of funding model that you're used to in an academic environment with NSF and things like that, where they'll put out a call for proposals, they'll take responses to those, and people will compete for that money. So when I'm recruiting students to Sandia, I say things like, it's nice to have base funding because you don't have to show up at Sandia and immediately write proposals and worry about how you're going to get funded. And we can be more strategic about how we invest that money to meet the mission needs. But then we can also compete for the Office of Science money. And so over the last 5 or 6 years, I've actually had a couple of really large projects funded out of the Office of Science in runtime systems and programming environments. So we have an opportunity to compete for that money as well. The science labs really hate it when we do that because they see it as their main source of funding. But we collaborate with them as much as we can. So just to juxtapose those two things. Now, there are differences. This is not the only funding that's available at the labs. So for example, there's DoD funding that we're sometimes able to go after as FFRDCs in the National Lab System. We can do that. And then you have projects like the Exascale Computing Project, which is sort of in DOE terms, it's actually a construction project. So they allocated funds to a construction project, and then those funds get sent out to the labs. They actually ran a proposal process for things like the application area and the software technology area in ECP, but it's a little bit different model of funding. And then there are things like earmarks and things like that that also get thrown in there. So most of what I'm going to talk about going forward is actually supporting the DOE model of funding. And so this program-driven kind of thing. Where do the programs come from? How do you initiate programs? How do you get funding to support these kind of programs? And because this is work that I've been doing in support of the DOE model. So last year, in early June, we were asked to come to Germantown, to DOE headquarters, and participate in what they were calling what was called an Extreme Heterogeneity Summit. And so over the last, couple of years, this has sort of been the process that DOE has followed to sort of motivate programs. They'll have a summit that they host somewhere. They'll invite people at the labs and occasionally other people that have some sort of support from DOE to come and talk about an area where they think a potential program or investment might be needed. So you can see the list of participants there from across the labs, science labs, NNSA labs included. And the subject was extreme heterogeneity. And so a lot of us showed up at that workshop not exactly knowing what extreme heterogeneity was. And so the discussion was, what is extreme heterogeneity? How important is this going to be going forward? Can we start thinking about some of the challenges in this area? Is there enough of a set of challenges for us to think about what a workshop might be? And then if so, can we start determining what topics we want to address at this workshop, figure out what a rough agenda would look like, identify key participants, and do some of those kind of things. And so we actually have a report, a short report that's about 5 pages that sort of summarizes our thinking around extreme heterogeneity that came out of this summit. So the next step in this was sort of, okay, let's talk about what the challenge of extreme heterogeneity really is. And this is a set of slides that I've stolen from John Schauf. I don't know if he's online watching or watching the video, but thanks, John, for the slides. So this talks about the fact that we have, if you look at our where hardware is going, right? So we have homogeneous machines, essentially, multi-core machines moving to many-core machines. Some of those many-core were accelerated with GPUs. If you look at where we're going in the future, we're likely to have more of those accelerators on a node simply because of power energy kinds of constraints. And then there's this sort of future of post-CMOS extreme heterogeneity that we were kind of focused on. Now, the challenge from a DOE perspective is there's a significant amount of work going on in the Exascale Computing Project that's already looking at things like heterogeneous machines and accelerators, right? And so if we're going to motivate a program, we have to actually look at a time frame that goes beyond ECP because there's already a significant investment there. And so we're trying to think out beyond Exascale. So if you think about the Exascale timeframe and being, sort of 2025 post-Exascale, where do we go beyond that? So we're trying to think about the challenges of extreme heterogeneity in sort of that timeframe. Then you look at things like this. So this is a smartphone system on a chip from 2016. And if you look at all the accelerators that are actually on that SoC, there's a thinking that this is the way that hardware will actually be going. Right now we have a small number of accelerators. We're using things like GPUs. There are already FPGAs that are being integrated into things. And so then you can think about, as it becomes easier to sort of design and fabricate SoCs, what's this going to do to HPC systems? Are there things we're going to be looking at specific accelerator technologies in the HPC space? And just to emphasize that, this other set of view graphs sort of looks at where we are now in terms of the technologies that are available to do computing, and we also have a whole bunch of new models of computation that are out there on the horizon as well. There's a lot of things going on in neuromorphic these days, right? So Intel just announced a new neuromorphic chip. We've got things like True North from IBM. A lot of that technology we're trying to figure out how to leverage that technology for high performance computing. And we see that trend sort of increasing. And so again, the time frame that we're looking at for extreme heterogeneity is where we are now, what exascale is going to cover in the next 6 or 7 years, and then what post-exascale is going to be looking at. And so wide variety of systems in terms of hardware, potential for lots of different kinds of accelerators. This is kind of the space of hardware that we're looking at. Does this make sense? Are you already thinking about what am I going to do for adaptive runtime systems and programming environments on these kind of systems?
I'm curious about your CMOS and general purpose circles there. I thought they would have been flipped. CMOS is kind of the voice, it's existing architecture.
Yeah, that axis is.
That's device technologies go up that
Yep.
way. And, okay, yeah.
Yep.
Yeah, we are thinking of lower left corners still.
Right. A lot of it, the challenge with this thinking is it's really hard to think about some of these things because it's so far out. This is typical DOE kinds of timeframes. We're only looking at a 5 to 7 year time frame. This is going out much further, and so it's a little bit more challenging to think about that. That's why I'm trying to engage the community and make sure that we're not missing something, get people's feedback on some of this stuff. Again, if you look at extreme specialization, to some extent this is already happening. This is just another motivating slide where if you look at a die photo of an Apple A8 kind of chip, there's already a significant number of accelerators on there, right? And we can see that kind of specialization happening in the commercial space. It's not going to be very long until we figure out how to take advantage of some of that technology in the HPC space, right? And we'll probably do it incrementally, but at some point we're going to have to figure out how to use this technology and adapt it to HPC needs. The interesting thing, just as a side story, Sanjay talked about my experience with networking. When we are doing networking research, we go talk to network vendors about the kinds of acceleration that we would want from a networking point of view. What can you put down on a network interface to actually accelerate some of the communications that we want to do, right? So we had this work that was presented at SC17 in collaboration with Torsten Heffler that was essentially about an active packet kind of model. When a packet comes in, I want to be able to process it with some application-specific function. And so we talked to network vendors about how to do that. And a lot of what we asked them for is not very exciting to them because they've got a whole bunch of accelerators that they've already got on their network that do video codecs and audio codecs and compression and security kinds of things. And so we sort of present to them, this is kind of what HPC needs if you're just doing MPI, we want to offload some matching and stuff like that. And then we describe it to them and they say, is that it? Is that all you guys want? Isn't there some more sophisticated kind of technology that you need? And you say no. And they look at their existing accelerator and they're like, well, we think we can do some of that stuff because it's sort of less complicated than what they're already doing. So in terms of answering this question of what is extreme heterogeneity, it's not just about hardware. We are concerned about this exponentially increasing parallelism, things that exascale computing is already looking at, but is getting worse. The end of Dennard scaling, the end of lithography, and so what's motivating some of these special purpose devices and accelerators? The data movement, increasingly hierarchical machine model. The cost of moving data now is much more expensive than it used to be in terms of power, energy, and cost, other costs as well. Or performance heterogeneity. So Sanjay already touched on this, right? The fact that all cores are not going to be created the same. Even on a node that's supposed to have some uniform set of cores and processing elements, the process by which you actually develop those things is going to lead to heterogeneity. And so you can't assume that everything is going to be uniform. Again, diversity of memory and storage technologies, emerging memory technologies, and the stall and disk performance is going to lead to disruptive changes in how we actually do storage. We're seeing that incrementally as well. And then a couple of things that we wanted to also think about in terms of diversity and heterogeneity are application requirements. I said about 5 years ago that workflow was taking over co-design as the DOE buzzword. It's still going strong. There's a lot of work going on in the community around workflows, scientific workflows, how you can take an application that is composed of multiple components, whether it be multiple simulations that are coupled together with analytics, and that kind of workflow, and map it onto a machine. There's a lot of work going on in that space, but we see that continuing. So there's a sort of broader set of applications that want to try to use these resources. And then to go along with that expanding set of applications that want to use these kind of resources, there's a significant number of non-experts that want to use these HPC systems. So these are more domain scientists that want to try to figure out how they can take their scientific workflow, the application that they've been working on in biology or in chemistry or something like that, where they've had some experience using these machines in a big data environment, which has sort of a much easier usage model, and then leverage HPC resources as well. And so we're not only looking at processing technology, memory technology, storage technology being more diverse, but we're looking at a broader set of applications and a broader set of users that may be wanting to use these systems. And from the DOE perspective, this fits really well into the model for a lot of the facilities that they have at the science labs, a lot of light sources that they have. There's really big computers sitting next to some of these scientific instruments, and they want to figure out a way to use those systems together. So from that, I don't expect you to read this, but from that Extreme Heterogeneity Summit report, we were given a charge letter from the Office of Science. So this is from Barb Helen, who's the director of Oscar within the Office of Science, sent a letter to Jeff Vedder, essentially said, Jeff, I want you to take charge on putting together this extreme heterogeneity workshop, and here's what we would like you to accomplish through this workshop. So this is the charge letter that we got from Barb. And so then we did planning for several months around this extreme heterogeneity workshop. So we had it in January, the 23rd through the 25th. It ended up being a virtual workshop because, as luck would have it, we got a government shutdown the day before the workshop was supposed to start. And so we actually had been anticipating this. Lucy Knoll, who is our program manager, sort of had this bad feeling about the timing of the government shutdown because she actually had planned a previous really large workshop in DOE that got shut down because of the government couldn't get its funding straight. And so she was really worried about this, and then it happened. We ended up having to do everything virtually, so we did everything online. And it actually worked fairly well. I don't know if any of you have participated in DOE workshops in the past, but we had a set of plenary talks that we sort of used over, just doing a WebEx where somebody presented things. And then we had breakout sessions where we had individual VTC connections for those breakouts. And we actually had to organize the content of the breakouts in a way because you can't just sort of have everybody talk all at once on a VTC. And so it was nice to be able to have people put topics into a Google Doc that they wanted to talk about and then cycle through everybody. And so give everybody a chance to talk. You couldn't have any one person dominate the discussion, Sanjay, which is good. And it actually went really well. So these were the breakout groups that we had. And you can see there, we had things like programming environments, data analytics and workflows, sort of the whole scope of things that we thought would be interesting from a extreme heterogeneity standpoint. And you can go to that URL there and look at the agenda and see the plenary speakers and things like that. So this was the organizing committee that put this extreme heterogeneity workshop together. So you can sort of map some of those areas back to the people that are responsible on the organizing committee. Again, Lucy Knoll is our program manager for this. So from my perspective, the breakouts that I ran were on OS and runtime systems. I actually had Mike Lang from Los Alamos help me with one of those. One of the breakout sessions looked at OS and resource management from a system scale perspective. So what do we need in terms of things to support workflows across a system? And then one of the sessions, the session that Mike ran, actually focused on sort of more node level resource management problems. And so we had lots of good discussion. There are notes from all of those breakouts I can point you to if you're interested in seeing any of those details. So that was kind of the lead up to this workshop. We had the summit, we had a report that came out of that, we had a charge letter that we were given, we had a virtual workshop for about 2.5 days. And then this committee then took all of that input, took all of those products that came out of that workshop and then started to work on a report, trying to summarize what the findings of that were, what some of the challenges are that we see that we're going to have to face. And then we started to think about priority research directions. And so what I'm going to talk about after this is what some of those priority research directions are in terms of OS and resource management. So I felt like I needed a safe harbor statement here. I'm not a vendor, so this is a little strange. But again, a lot of what we discussed both during the workshop, after the workshop in terms of the output that came out, what some of these priority research directions are, this is all my view on this, right? So I'm not really speaking for anybody else that's on the organizing committee or for Lucy or for Oscar or for DOE or anything like that. This is just what I've been working on. This is my perspective on things, and I just want to emphasize that. Again, we're working on a final report. I don't know how the final report's going to come out. There is a possibility that we share that with Oscar leadership and they're not happy with it or they want us to emphasize other things. And so I just want to have some kind of disclaimer, especially since I'm online and I'm recorded, that this is really my perspective on things. So this is a set of slides I actually gave during the workshop about my perspective on things from an OS perspective. OS and resource management perspective. So this is a little cartoon that I've been using for, more than a decade that sort of describes how I view things that impact operating system R&D. And so we have things like applications that can influence what the OS provides. There's a usage model that comes along with that, and this is really about the system and how you expect to use some of these systems. Again, things like batch, scheduled, space shared, has been our usage model for a long time. There's obviously an influence from the architecture underneath us. As hardware changes and capabilities evolve, that changes the way the OS behaves. If you know anything about what's going on with Spectre and Meltdown, when things happen at the hardware layer, it can definitely influence what the operating system does and how it responds to hardware changes. Shared services is a little bit harder to describe, but this is things in HPC that you can think of like a parallel file system that exists somewhere else, or you can think of an instrument somewhere where you're getting data streaming onto the machine, changes the usage model, influences the way you want to provide services from an OS perspective. And then the most challenging aspect of operating systems, from my view, has been history. There's a lot of history that goes into how you need to support applications and application and development environments on an operating system, right? This is why we've been using Linux and Unix operating systems for several decades, because they have all of the features and all of the standards that most people are used to. And I can tell you from someone who's spent a career developing lightweight operating systems that try to get rid of that stuff, it's much harder to do that because of the different standards that we have. And the history that's there. So anyway, again, if you look at architecture, so from an architecture standpoint, we've got things like SOCs, hardware specialization. How do we make the OS and the runtime system aware of these kind of capabilities? You can even think about accelerators that are just there for the operating system, right? So these accelerators don't necessarily need to be there just to serve applications. There are parts of an operating system you may actually want to offload to accelerators to think about how that would work. So there's some of those kind of challenges. You think about some of the task graphs and how you would optimize a task graph in a runtime system. Can you build a specific set of hardware resources to do that? I don't know, but that's certainly something that would be interesting to look at. A single node may not be a single cache coherent physical address space. In many ways, that's true today. If you attach your GPU in a way that's not very efficient, you get these multiple different address spaces that aren't coherent. I will say that there are technologies that are trying to expand that space of coherency as well, which provides some interesting capabilities, but also challenges to go with that. And I mentioned that in context of things like photonic interconnects, right? So photonic interconnects has always been out there as one of those things that's always going to be just around the corner. You would think in about 10 years that technology may actually be available. And so this isn't really going to help you from a latency standpoint, but from a bandwidth standpoint, to have a memory resource that's on the other side of the machine that you can access at very high bandwidth. How does that change the way your operating system looks or your resource management takes place? There's work going on in more intelligent memory controllers. Again, some of these things like exposing page tables to the application directly rather than having the OS manage them. There's some interesting things that you can do there. And this idea that if you look at what's going on a node right now with things like networks on chip, a lot of the nodes look like racks used to look like in the past. And you can just take that analogy and keep expanding it, right? Nodes will look more like racks will look more like systems will look more like much larger distributed systems. We've already seen, just going to exascale, that things like, we used to have a machine that was mostly aimed at doing computation, one that was doing visualization, one that was doing analytics. Those are being subsumed onto the machine now, right? This is the reason people want to run more sophisticated workflows, because all of those kind of systems are now available on one system. You used to have a separate parallel file system. That's been subsumed onto the machine now in things like burst buffers, right? And so we think that kind of model is going to continue to happen. Special purpose systems, again, are going to start to be more general. How do you design an OS when you know there's going to be special purpose devices there? How do you do those kind of resource allocations? Can you virtualize those special purpose devices in some way, right? So if you look at GPUs today, it's really hard to virtualize them, but people have been working on that technology now for several years. Can you take a GPU and share it among multiple users or multiple applications in a workflow? And then our trust model will have to probably evolve. Security is one of those things that we haven't really paid a whole lot of attention to in HPC just because of the way that we use the systems. But that's potentially going to change going forward with the different, more sophisticated usage models that we want to try to enable. Again, I talked a little bit about this already from an applications perspective. We have an increased complexity. One of the things that's going on in HPC is I think we're trying to settle in on layers of abstraction that much more easily support mapping to different architectures. If you look at the abstraction layers that have been developed in HPC, a lot of our abstraction layers have been bottom up because we want to try to stay as close as we can to the hardware to get performance. So if you look at things like MPI as an abstraction layer, MPI abstracts the network. It doesn't abstract data movement. It abstracts the network, right? And if you want to try to abstract data movement, MPI is probably too low level for that because we've got too much inherent in that abstraction to try to do anything to try to raise it up. If you look at the big data community and those kind of communities where they've actually looked at abstracting the applications first. How do you build up applications? How do you do things like MapReduce? That's a nice abstraction layer at the application level. And then they try to figure out how to map that to the machine. We've done sort of the opposite because we're worried about performance. But I think those abstraction layers are going to continue to evolve to provide a way that we can map more easily to a diverse set of hardware. Then there are things like access to system services from an application layer. One of the things we have to do at the OS level is support all the system calls that Linux has. The system call model has really been around for a long time and is probably not the most efficient way to service things like task-based programming models. You trap into the OS, the thread goes away, context switch. It's a pretty heavyweight operation for most of the lightweight computing that we want to do. So we can think about what's the real most efficient way to get system services and communicate between the application and the system. And then we never want to forget about tools from an application perspective. From an OS, looking up from the OS, tools are just as much applications as applications are. And a lot of the capability that we've been trying to provide at the OS layer is actually motivated more by providing services for tools than for applications. Most applications don't really call system calls if they want to scale. But a lot of the things that we need to provide from an OS perspective are to support tools. What else do I want to say? And the only other thing I'll say is that we really need, I think we're going to have to focus more on an event-driven model. This goes to some of the message-driven kinds of things that Sanjay talked about. One of the challenges that we have with things like MPI and how to integrate fault tolerance into MPI And the reason it's so challenging is because MPI fundamentally isn't event-driven. And most of the models that we need for fault tolerance have to be event-driven. And so there's going to be sort of a move, I think, to think about how applications can be made more event-driven and how some of the services that are provided will support that. From a usage model, I said some of this, we need to move beyond sort of just the batch scheduled space shared non-interactive job model that doesn't fit with a lot of the way that people want to use these machines. We need to figure out a way to provide dedicated as well as shared resources. The challenge here goes just beyond the technical. There are things like how do you, what does a cost model for charging for time on a machine look like when you're being much more sophisticated about how the machine's being used, right? It's easy right now to stick with node hours, and we charge for node hours, and we know how to count that. If you're doing more sophisticated workflows, or you're allocating parts of the machine, or you're migrating services around, or parts of an application around, there's not really a good way to think about from a facility standpoint of how you charge for those cycles. And so there are things like that as well. I'm going to talk about a little bit more about this implicit versus explicit allocation of management resources. The way I like to characterize this, and I do it in a couple places in this talk, I think, is we spend a significant amount of time mapping an application to a machine, right? And so when you go to run an MPI code or a Charm++ code, you have to explicitly allocate nodes. You have to think about how many threads you want on a core, how many ranks you want on a core, where the memory gets placed relative to where those cores are. There was an applications talk at Sandia a couple of weeks ago on our one of our ATDM applications, mapping it to Trinity. Trinity's half Haswell and half KNL. And so they wanted to run a simulation across both sides of that machine. They had to do a significant amount of effort to figure out what's the problem size that goes on the Haswell, what's the problem size that then can be mapped to the KNL, how many KNL, on a KNL, how many ranks do you have per core, how many threads do you have per core? Completely different, but it took them a series of studies from the application perspective to figure out how to run that application across that machine. And I can see the complexity of future machines is going to make that, we can't tolerate that. It's just going to be too complex. And so the way I like to characterize this is instead of mapping the application to the machine, we're going to have to figure out ways to map the machine to the application. You're going to have to be given sort of an application view of the problem that you want to solve, and then the system itself is actually going to figure out how to best use the available resources that are there to solve what the application actually wants to do. There's some other things here about usage model, but I'll go on. And then shared services, if you think about most of our large-scale machines, they have these RAS systems that are built around them to help with the health of the machine. There's a significant amount of instrumentation and analysis that comes with those. We need to be able to leverage these capabilities going forward. And so I see the RAS system as one of those shared services that you're going to want to take advantage of from multiple places. This is, in the short term, one of the things that we don't do is really leverage these for fault tolerance. This is the part of a big system where when a node goes up or a network link goes down, when a node goes down or a network link goes down, it knows about it, but the system software doesn't actually get notified of that kind of stuff. And so we can think about sort of a RAS system as being one of these shared services. And then there's a whole bunch of external resources that people are looking at coming into the machine in terms of connectivity to networks and storage, streaming data from external instruments I mentioned, and then new ways of actually getting, you can think about things like graph problems. How do I run a big graph problem? Well, the first problem I have is I have to ingest it onto the machine. And so there are some things like capabilities that we need to think about from that perspective. And then history, legacy programming interfaces. We've been dealing with POSIX for a long time. We've been trying to get rid of POSIX in the I/O system for a long time. We're probably going to get rid of POSIX in other places. One of the challenges we have from an OS perspective right now is it's not Linux that defines what the environment is from an application perspective. It's actually glibc. glibc is more of a barrier to doing OS things than the applications are. Again, applications don't necessarily make system calls that often or rely on system behavior, but glibc does a lot of that. It imposes a lot of functionality that the OS needs to provide. I mentioned standard protocols already. It's going to be hard to deal with some of that going forward, and so we'll have to look at what are the abstraction layers for some of these things and what makes sense rather than just the standard that may be there. And then, we may have to move away from a Unix model. I know that's, could be very challenging, but when you're thinking 10 years out, some of the things that we see coming around, everything may not just be a file. You may not just get a file descriptor for everything. And so we need to think about some of those kind of things. All right, so at this point I figured I would be boring and I would have to actually engage you guys in some aspect to make sure you weren't falling asleep, that you were responsive. So I threw in a pop quiz. So the question is, which of the following is most important factor in determining whether or not a technology is adopted by Sandia application developers? So this is really twofold. This is to keep you guys engaged, and this is for me to pick on Sandia application developers. So your choices are performance, scalability, maturity, sustainability, ease of integration, or testability. So I'm going to go through each one of these. If you think this is the most important one, feel free to raise your hand. So who thinks performance is the most important factor? Okay. Scalability, maturity, okay. Sustainability, okay. Ease of integration, okay. Testability. All right, for the most part, you guys did pretty well because it's sustainability. Application developers were more, they want to develop technologies that they know are going to be there in the future. And they don't care how well they perform today. They don't care how well they scale.
I didn't see portability on the list. Is that sustainability?
So in some ways, the reason it's not there is because I wasn't exactly sure how to differentiate it from some of these other ones that are here. Because ease of integration and sustainability, I think there's an aspect of those in portability, but I wasn't sure how to differentiate it. And I thought if I put portability in, everybody would say portability. And so I was trying to help by not putting portability in here. But in some ways, people use, so from my perspective, I think MPI was really successful because it was sustainable. It was written into the vendor contracts. Once you had an application using MPI, the support for it was going to be there. And so, again, this is one of those things where if that technology didn't work really well, over time, people expected that it would. And so there was an expectation that it would work well. And MPI, if you look at how MPI was integrated into existing applications, the interesting thing is that all of the DOE applications that I went to Sandia to work with that were porting to MPI, they already had a message passing layer. They had a message passing layer that had NX, P4, they already had an abstraction layer in their code for message passing, and MPI was just plugged into that. And so it was a really easy thing for them to do, and it was just over time, those support for those other messaging layers kind of just went away, and it just became MPI. But the portability aspect of it was already built into the code, and so it was a pretty easy thing for them to do. This is mostly about my frustration with application developers at Sandia. When I try to get them engaged on doing things from an OS perspective or from a networking perspective, the pushback I get is if what you're doing isn't going to exist in the future or is going to be different on different machines or things like that, I don't care. I want to know that there's going to be some path to sustain the technology that you're developing that is going to be there and support me in the future. And the other thing that comes from this is I have seen, I've tried to work with application developers to get them to make the change to the code, and it's been a struggle. And then something brand new will show up in a C++ language standard, and the next day they're using it. And so I turn around and I say, what am I doing wrong trying to work with you guys on this technology? And they say, well, it's C++. The vendors are going to have to support it. It's going to be there. It sucks today, but we're going to give them feedback, and then they're going to work it out over time. And so that's a very frustrating thing to do from a system software perspective, but I understand why it is. And so if you look at a lot of the technologies that people are developing, while they're interesting, you have to think about what's that path to sustainability. How am I going to get this technology in a way that the application developers will actually want to use it, want to leverage it, and want to stick with it? Yeah?
Yeah, they seem to take to Python in spite of this Python 2 to 3 developer.
Yeah, so I can't explain everything. I can't explain all of that. But this is just one thing I see. If they think there's a path to sustainability, they're much more likely to put effort into it. And for things like Python, where there's a much larger community, that they think is going to sustain this, then that may be some of the motivation that comes from that. Okay, so on to these priority research directions, and I'm running a little bit behind, but I'll try to get through this. So we spent a significant amount of time trying to figure out at a high level what are these priority research directions that we're going to try to pursue around extreme heterogeneity. And so the wording here is we worked on quite a bit. I hope you're going to like this. So we wanted to reduce time to verifiable discovery despite diverse application domains and an exponential increase in architectural complexity from rapidly changing heterogeneous systems. And then we looked at these areas, so maintaining and improving programmer productivity, managing resources intelligently, modeling and predicting performance, enabling reproducible science despite non-determinism and asynchrony, and facilitating data management, analytics, and workflows. And so these are sort of the priority research directions that we developed, and there are details under each one of those that sort of succinctly try to describe what those areas are looking at. And so let me dive down into managing resources intelligently. So from an OS runtime system design, hardware resources are becoming complex and diverse. The OS and the runtime system must figure out how to integrate special purpose devices and accelerators, and we can't assume all the resources on a node are identical and dedicated, right? So how do we share those resources? How do we isolate those resources? This is the challenge that an OS has, but how do you design an OS when you know that you're going to have future devices that are special purpose that need to be integrated? How do you make the OS aware of how to use those devices, how to virtualize those devices, how to share and isolate those devices? And so I think there's some fundamental OS design work that has to go into some of this. And we've seen some steps that people are taking along the way to do this, but I think it's going to continue to be a motivating challenge going forward. And the thing that you don't want to have to do is rewrite your OS every time something new comes along, right? And you can think about things like the device model of using an accelerator. Really doesn't work very well, right? It's a special purpose, application-specific, dedicated thing on the side that's over a far-reaching bus that has a separate address space. Not going to be like that in the future, right? People are working on memory technologies right now that integrate these things much more tightly. You can think about the coherent space, address space extending much broader. How do you design an OS that is aware of that and can take advantage of it? And then along with this, there's this capability for dynamic discovery of resources, not only because you can't power and supply power to all of the components that could potentially be there. There's going to be restrictions on availability again. Things will come and go. We're still trying to think about resilience kinds of aspects of this. But how do you have an OS design that is much more adaptive and dynamic, where it can discover what resources are available and figure out how to map those to the application in a way that makes sense. The next one was decentralized resource management. So scalable methods of coordinating resources that allow policy decisions and mechanisms to coexist throughout the system. If you look at a lot of the hardware today, the hardware is being built with its own intelligence. So you can think about things like adaptive routing or adaptive power management, where the hardware is actually trying to make optimizations and figure out what it should be doing. In the future, you have the OS and the runtime system trying to adapt resources. You have the hardware trying to adapt resources. Who made decisions about those resources and when they made them and what the effect is going to be much more complex, right? This is why we're looking at things like temporal non-determinism and saying, how do you do performance optimization in the face of temporal non-determinism? If you can't run a code reliably and get sort of the same ballpark, how do you optimize it? Well, we're going to have the same challenge when we push that kind of optimization down into the hardware and down into the software. How do you do that? How do you do performance optimization, resource optimization, especially if there's not a human in the loop? So you look at, the system software has to coordinate resources across multiple levels, disparate devices in the system. We can't assume that we have full ownership of all the resources in some cases where you have dedicated resources that are application specific. How do you do that? And again, there's this idea that we have to be introspective, right? Instead of doing things post-mortem where you run a code and you look at a trace and you figure out what you can optimize and you go back in and make changes and then run it again. We kind of want that cycle to happen automatically from a system software perspective. Can we build enough instrumentation into the runtime system and into the OS to actually figure out how to adapt and use those resources more efficiently. This involves not only the pieces of the operating system and the hardware and the runtime system, but also communication with the application. Do we have the right abstraction layers at the application to be able to have a flow of information back and forth among all these elements to be able to do things optimally? And then the last one was autonomous resource optimization. Again, a lot of this kind of thinking, but are there things that we can apply, like machine learning, because that's a buzzword that DOE likes at this point. Can you figure out how to use machine learning to do some of this optimization, right? And this goes to that thing where I said, we need to figure out ways to map the machine to the application rather than vice versa. Can we discover the resources that are there? Can we discover from an application what it needs to accomplish? And then do some kind of sophisticated way to map those resources so that everything doesn't have to be explicit. Because the diversity of machines that people are going to be running on, there's no way to have sort of a view of the system from an application developer standpoint that will say, here's how you map the resources of your application out of this machine. It's just going to be too complex to do that. Okay, so this goes into my next complaint about application developers. So just let me pause there. Did those sort of priority resource directions resonate with people? Did they make sense? Are there things that you think we're not really addressing that need to be addressed from that perspective? Are there challenges that we're missing? You don't have to think about it now, but let this settle in. I'm going to be here for the next 2 days, so if you have any comments, yeah?
Can you give a more concrete example of what you mean by the mapping resources? Go beyond the batch schedule based shared model? Or is it, how do you schedule that? And is it when you enter availability of resources? When you enter availability of the resource into the equation, how do you balance that? And what do you have in mind? Just a scheduler, and it goes back and says, I don't have enough of this resource. I'm going to go back and recompile and build for some other resource that's available right now.
So I'm thinking about things like elastic resources, where if you look at some of the stuff that the big data community does, where you say, MapReduce, right? Here's the problem. Do you determine how many nodes in the system get used because of the results of one of those stages versus the other? Right? Between those different stages of the computation, the resources grow and shrink based on what the results are. And as you have these higher level abstractions in a workflow that move from one phase of the computation to the next phase, your resources may change, right? You may have to expand a set of resources because of the output of one stage. You may then do a reduction on those, on the data and on the problem that you're looking at that doesn't require as many resources in the next stage. And so I think about it initially from that perspective, right? I've got this more complex workflow where it's not just the entire app that's going to need 5,000 nodes. It's, well, I'm going to start out with something that's sized to the problem that I want to look at, but that problem could potentially grow and shrink as we go through the different steps of the workflow. And so does a usage model where I allocate 5,000, but I really don't, that's the max I need, does that really make sense? And so it's how do we figure out as we're going along through the different stages of this more complex workflow, what resources really need to be dedicated to the parts of those components in the workflow. That's the kind of model I'm thinking about. Does that make sense?
Yeah, I think so.
Okay, so this is my next set of complaints. Exploring potential solutions. So this is the stuff that drives me crazy when I'm trying to think long term about how we do things and some of the challenges that are out there. So these are the quotes. These are actual quotes. We'll explore that using that feature when it gets into the standard. And I say to our application developers, how do you think things get into the standard? They don't get into the standard until we actually know that they work and that they're effective and that they make sense. And so we can't get things into the standard until we actually have that data. And so we actually have to work with you to figure out, is this the right thing? Are we doing this the right way? Does this make sense? Will applications be able to use it? Can we implement it in a lot of places that make sense? And so this is the cart before the horse kind of thing. You can't say, I'll just wait till that gets into the standard and use it. There has to be a process by which we collaborate to figure out what needs to be there to do this. And similarly, we'll consider task-based models when it's clear MPI everywhere won't work anymore. So this is the thing where I'm going to stick my head in the sand. I'm going to ignore any kind of potential problems. And then when I do recognize there's a problem, I'm going to pull my head out, and you better have an answer, and I better like it. And I say, you can't do that. You actually have to work with us to figure out what's the space of solutions that really make sense for your application, right? There are all these technologies that are addressing some of these problems. We don't know how well they work from an application standpoint because we can't get enough of your attention to figure that out. And so you really need to work with us to figure that out. And you can't just say, I'm going to keep going until MPI everywhere stops working, and then I'm going to try to figure out what to do. That's really the wrong attitude. And so what I'm looking for from an applications community, and this is something that I look to for Charm++ and the things that you guys are doing, is can we evaluate some of these technologies and at least have some path by which we understand how well they work, and then over time iterate on those so that we can actually figure out how to make them work well. Because it's too late when you do stuff like that. We have to continuously engage the exploration and evaluation of technologies. Otherwise, these solutions aren't going to be ready when people want them. The important part here is we have to provide a path that's incremental, right? So we have to provide ways for them to incrementally adopt and evaluate some of these technologies. And that's the biggest problem that we have, especially at Sandia and within the NNSA, I think. We have codes that are, for the last 20 years, they've been MPI codes with several $1 billion of investment in them. And those codes are not going to go away anytime soon, but they need to be able to figure out how to incrementally adopt some of the technologies that are coming along. I have a whole list of issues and concerns here that I'm not going to go through. I'll page through them, but they're all things that I worry about from a runtime system perspective in terms of challenges that we have just making things work from an OS runtime perspective. So I sort of flew through those, but again, I'm happy to talk about those. You can look at those. The slides are going to be online, I think, so you can page through some of those if you have any questions about some of that stuff. I'm happy to talk about it. Just acknowledgements. So this is, again, the workshop organizing committee. A lot of discussions with the participants in the breakout group around OS resource management for the 2-day workshop, 2.5-day workshop that we had. And again, I stole some slides from John Schauf without his knowledge, so hopefully he's okay with me showing those. And at this point, I'm happy to take any questions or comments. Thank you.
Thank you, Ron. And time for additional questions? Yes.
I have lots and lots of questions, but I'll just pick my top one.
Okay.
If you look at the top 500 list from November, you'll find that the fastest supercomputer in the world is 3 times faster than the number 2 and 5 times faster than the top US system, which is Titan. Yet, the top system in the world is completely homogeneous, right? So it's an interesting question of how much time do we want to spend on heterogeneous acceleration systems versus designing from the ground up, just like the Sunway system is, right? I mean, it's completely independently designed. Can we keep scaling x86? Can we put accelerators in and be able to keep up with these homegrown systems?
So yeah, I think that's a really good question. I think the trend is, and if you look at the Chinese, they're trending towards heterogeneous systems as well, right? They've got accelerators where they're designing their own accelerators for those machines, right? Right. Number 2 is built of those machines of heterogeneous parts, and I think people are looking at the number 1 machine and thinking that probably is not going to last. That trend is not going to last very long, just because of the way the technology is going in terms of Moore's law and the energy efficiency that you can get out of accelerators. Right. So I haven't looked at the energy numbers when you compare the top 500 systems in terms of energy use. But my guess is number 1 is probably not the most efficient in terms of energy use. And if you look at number 2, it might actually be much more efficient. And so I think those are the kind of numbers that where people are looking at the systems and going, yes, we could build something like that, but we can't sustain the power energy investment that's going to be needed to support it. And so I think that's where a lot of the economics of it are coming from.
Is the energy efficiency issue?
Is the energy efficiency issue a capacity issue or the expense issue? Like, we don't want to spend $50 million paying for the electricity bill?
I think it's both. I think it's, you're going to need another couple of substations in order to get the 30 plus megawatts that you need for these machines. And that investment is high. And then the $1 million a megawatt hour for these big machines the budget of $30+ million a year to operate these is very high. And so people are looking at, can I get a much more energy efficient system where I don't have to worry about having multiple substations and 30 megawatts and $30 million a year powering them.
So, question about the system on a chip and utilizing them. So, as Sanjay said, it's not. We're not designing the nodes, right? The nodes are getting fast because of consumer needs.
Yep.
And so the question is, right? We're not going to be getting the hardware that's being designed from our applications, but. I'm trying to say, so the GPU, all those special systems were put there because they're needed by your cell phone.
Right.
And so would it be better to say, take your application and say, many applications are sort of these multi-physics things.
Sure.
And so you could think, okay, let's just, from the application, let's divide it up into things that will fit on the various pieces of hardware we have.
So,
is that a sensible thing to do? You're
sure.
saying sort of not so much.
Let me give you a path. So we're seeing FPGAs be integrated into a lot of components coming, right? So Intel's got a roadmap where they've got FPGAs integrated onto their processors, right? And so we can see a path where application developers then start writing codes for FPGAs. And so you've got very application sort of specific acceleration in an FPGA. And then what the trend is, after most people figure out how to implement stuff in an FPGA, is they figure out how to go fab it, right? And so you can see a path where the HPC community says, hey, everybody's got these sort of common things that they're doing to accelerate things like linear algebra or solvers or these other aspects of applications that most of the applications use. We've now put those into FPGAs, and we can actually figure out a way to make ASICs that go with those, or have SoC designs that now we have an IP module that used to do that, right? It used to be a thing that was on an FPGA, but now it's an IP module that you can go buy and integrate to your SoC. And so there's a path there where I think you're right. We're going to figure out how to take those pieces of the application and fit them together. But then eventually people are going to figure out how to accelerate those pieces on the different hardware things that are going to be available in the future. And so I think that's the path where people are saying, we could actually do this. We could build SoCs that have these specific accelerations, because that's what's been done in the past for mobile phones. It was, hey, we're going to take this MP3 player, put it in an FPGA, but then we can take it and fab it and make an IP block for it and just put the IP block down on an SoC. So.
There's economies of scale, right? But if you can do that for commercial devices, maybe you do have a fab.
So actually, Sandia does have a fab, but we don't anticipate having to fab those. We're just looking at. So there are people that are saying, we do a lot of things to lower our cost by buying commodity. So let's take GPUs. So we bought commodity systems with GPUs in them. And then, so we made an investment in a machine like Titan at Oak Ridge, where it was much more cost effective to buy a GPU-based system to get a Linpack number, okay? And then we spent a significant amount of investment getting applications to actually use those effectively. And not all of them are actually doing it yet. And so it was 10 years of, we're at about 10 years of investment from an applications perspective to make those work well. And so there's this question of, did we really get the economics of a lower cost because we went with commodity, given all the investment that the communities had to make in that? And so if you take a step back and say, maybe we're more cost effective at actually designing stuff that we know we can take advantage of with much less impact on applications. We already have abstractions for things like linear solvers and linear algebra kinds of things. Can we build those abstraction layers into hardware and get much more effective systems at a much lower cost, because the hardware is actually being designed to fit the applications rather than the applications designed to fit the hardware. And I don't, that's a question that's open for debate. And we're just saying, I think there's a path to explore some of these things. And, just like Intel providing us FPGA capabilities we didn't ask for that, but we're going to have to figure out how to use it. And I think people are seeing those kind of things continue to happen, where there's going to be accelerators on a machine. We're going to have neuromorphic accelerators that come on nodes, because that's what the big data community is going to want to use. How do we take advantage of that from a scientific computing standpoint? And so we don't determine what they give us, but we're going to have to be prepared for it. And the challenge here is, if we know it's GPUs and it takes us 10 years, and this was on one of the slides, if we get a neuromorphic accelerator or something else, are we going to have to spend 10 years for every accelerator that we get? It doesn't make a lot of sense.
So we need to stop quickly, but one of the things they touched upon in resource management, all these flexible resource management things you talked about, I mean, this seems like a self-serving question, but I mean it somewhat genuinely. Are there technologies out there other than, with CHAM++ and AMPI, we can do this shrink expand thing to deal with the fact that you give me number of nodes and you change the number of nodes in the middle and so on. But there must be other ways in which you are envisaging that happens without using CHAM++ and AMPI as well.
I'm generally thinking about things where we have to have some abstraction layer that allows us to not have an explicit mapping of resources, right? That things can move around, things can migrate, things can come and go. We don't really have in HPC that kind of model. We have some of these task-based models that will do that sort of within an initial allocation. They can stick to that, but then we're not really flexible outside of that. And so, except
CHAM++ and AMPI can do that today. So, okay.
So, but
just to make sure.
Even there, I think you're constrained by what the scheduler gives you, right? You get a set of nodes.
When we write our own schedulers for that, yes, we are constrained by the schedulers.
Right.
Yes.
And I'm thinking that's an arbitrary sort of constraint that we have on our systems today that may not be there in the future.
One last question,
All
I
right.
think.
So, I think your characterization of application developer, scientific user, is true. We do stick our head in the sand a bit, and
Sure.
we don't want to do this thing until the world is on fire. But you didn't explain why we behave this way. I mean, if maybe we're lazy or something, but it's just the hardware keeps changing, and it's very hard for me as a scientist writing science grants to spend 3 years rewriting the same algorithm to run on a computer to generate one paper for the student. It's just like, this is crazy, okay? And so that's why I stick my head in the sand until the world is actually on fire.
Sure.
Right? And then it's like, and the things is, over our career, we've seen these computers, they keep changing. And it was like, the next thing, we're going to retool all our codes for the MPI.
Yep.
I'm going to retool all our codes for GPU. And it's like,
Right.
no. Either somebody else should worry about it and I'll collaborate with them, or frankly, I will literally wait till the house is on fire and it's like actually something to worry about.
Yeah, I was simply trying to point out that this is sort of a vicious circle, which is at some point we need to engage the application developer so you don't have to worry about these kind of things. That we can provide you with abstraction layers that actually will work for the problems that you want to solve without you having to write something specific to the machine every time. And getting to those abstraction layers and getting to those things that are important from an algorithmic and application perspective, we can't do by ourselves. And so when you just pull your head up and say, okay, I need the solution now, you're probably not going to be happy with what we try to give you because we haven't been engaged along the process. And so I'm just trying to point out that we need to figure out ways to engage the applications community so that we actually have effective solutions when you do pull your head out of the sand, or pull it out just every once in a while so that we can make sure that happens.
I think the kind of question that would engage me to start talking to someone like you, it would be like, if you come to me and ask this question, what is it that I should offer you that you will rewrite your code and then never do it again for 15 years? And if you can say something to me and I can get excited about that, then I'm willing to put in the effort. But otherwise, it's like, your code sucks on whatever, exascale. I'm like, yeah, it sucked on everything because I can never rewrite it for the latest machine.
Yeah. No, I understand.
Yep, I think valid point, worth some discussion in the break. So speaking of the break, thank you, Ron.
Thanks.
Yep. And we'll take